What's up, everybody? This is Wallace from A3Academy. Got some good news. Even though we sold our company car, the Ferrari, from before, we got a new one. It's the Bugatti Veyron Grand Sport. Pete really wanted to get the Super Sport, but I told him that the most important part of maintaining a successful company is to never overspend on things like cars. So today we're going to be talking about Le Chatelier's principle. And Le Chatelier's principle is an important thing to know in chemistry. It's used a lot in a bunch of different industrial processes. So yeah, it has a pretty big impact on chemical reactions. So Le Chatelier's principle states that if a system at chemical equilibrium undergoes a physical change, then the equilibrium will shift to counteract the change. So that basically means that if you physically change a system in equilibrium, then that system will try and reverse the changes that you just made. So one of the physical changes that can affect the equilibrium of a system is a change in concentration. You can create a change in concentration just by adding or taking away reactants or products. So suppose we had this equation in equilibrium. The reactant is A and the products are B and C. Suppose that we added some of the reactant, A. So we have a lot of A. Le Chatelier's principle tells us that the equilibrium will shift toward B and C, which are the products, so that it'll counteract the fact that I just added a lot of the A, which is the reactant. Whenever you change the concentration of one of the reactants or products, Le Chatelier's principle states that the equilibrium will shift in the direction with the now lower concentration, so that it'll kind of counterbalance the change in concentration. Another type of physical change we can put on a system in equilibrium is a change in temperature. If we had an equation in equilibrium, and we knew that this equation was, say, exothermic, that means that the delta H of the equation is negative. But more importantly, we know that heat is created as a product. If we increase the temperature of the system, then it'll create extra heat. And so that extra heat will be used to push the equilibrium toward the reactant side, or A. So if we increase the temperature in an exothermic reaction, then it will become more reactant favored. On the other hand, if we decrease the temperature in an exothermic reaction, we will make the reaction more product favored. In the same way, if we had an endothermic reaction, delta H is positive, then heat will be included as one of the reactants. And so a decrease in temperature will cause the reaction to become more reactant favored. And an increase in temperature will be an increase in heat, and it will cause the equilibrium to shift over to the product side. So whether or not an increase in temperature will cause the reaction to become more reactant favored or product favored depends on the sign of delta H. Because if delta H is positive, then the reaction is endothermic, and that means that an increase in temperature will cause the reaction to become more product favored. However, if delta H is negative, then the reaction will be exothermic, and that will cause an increase in temperature to make the reaction more reactant favored. So this relation is mathematically shown using this formula right here. This is called the Van Hoff differential equation, and it basically tells us how the equilibrium constant K will change when the temperature of the system changes. So delta H is the standard enthalpy of the reaction, R is the ideal gas constant, and T is the temperature of the system. And by analyzing this equation, we can find out how delta H influences how K, the equilibrium constant, will vary with temperature. Now, another way we can change the system's physical characteristics is by changing the pressure or the volume. Now we know Boyle's law, pressure and volume are inversely proportional, which means that an increase in pressure will mean a decrease in volume and the other way around. So if we had an equation like this, we notice that there are more moles of stuff on the product side than there are on the reactant side. Specifically, there are 2 moles of stuff on the product side per 1 mole of stuff on the reactant side, because there are 2 molecules on the right and 1 molecule on the left. If there's more moles of stuff on the right side, then that means that the right side will have a greater partial pressure. Now, if we increase the pressure of the system, then Le Chatelier's principle will cause the equilibrium to shift to the side with the lesser partial pressure, which means that when we increase the pressure, or at the same time decrease the volume, the equilibrium will shift to the side with less molecules. And in the same way, if we decrease the pressure, the equilibrium will shift to the side with more molecules. And again, a decrease in pressure is the same as an increase in volume. So those are the ways that we can change physically a system in order to shift the equilibrium. So let's take a look at an actual example. So this equation right here is the equation for the rusting of iron. So analyzing the different molecules in this equation, how do we find out what happens if, say, we removed H2? Well, when we remove H2, the concentration of H2 will decrease. And since the concentration decreased, that means that Le Chatelier's principle will shift the equilibrium toward the product side to make up for that lost H2. Now, what happens if, say, we decrease the temperature? Well, we can't know the answer to that question without knowing that the rusting of iron is actually exothermic, so delta H is negative. So if you know that the rusting of iron, this equation here, is exothermic, that means that we know that heat is a product. And when we decrease the temperature, that means that we are decreasing heat, and therefore Le Chatelier's principle will cause the equilibrium to compensate by being shifted towards the product side. The equilibrium shifts to the right. Now, what happens if we, for example, increase the volume? Well, when we increase the volume, that means we're decreasing the pressure. So Le Chatelier's principle will compensate by shifting the equilibrium to the side with the higher partial pressures. Since the side with the higher partial pressures is the same as the side with the greater amount of moles, we have 7 moles on the left side and 5 moles on the right side. So the reactant side has a higher partial pressure, which means that the equilibrium will shift to that side. So it'll shift to the reaction side and will become more reactant favored. So those are the basic principles of Le Chatelier's principle. That's all for today. I'm Wallace from A3Academy. Remember to subscribe to us on YouTube and also like us up on Facebook and Twitter. And as always, the more you know, the better you are.
Drop down off the drop.